Thanks, Tim.
Sylvia, yeah, you got your camera on? Thank you.
Yeah, a good thing. Thanks, Tim. I'm going to spend the next 10 minutes talking to you about a fascinating material called zeolites and about how our company ZeoTech is going to have global impact, particularly with clean tech applications for zeolites. So zeolites are a natural material that were first discovered in the 18th century, and they are aluminosilicates that have a porous structure. And about 80 years ago, work was done that proved that you could synthesize zeolites with a very predictable pore structure. Predictable in that the pore structures were exactly a particular size. So for example, if you talk about a zeolite 4A, that means the pore structure is 4 angstrom, an angstrom being about 1/10 of a nanometer. And this very ordered pore structure meant that those materials started to be called molecular sieves, because you could literally sieve out molecules using this structure. And then over the last 80 years, a growing number of applications that use this fascinating material are having a big impact in the clean tech sector. So you can see on the right of the picture there, that's something like what the structure looks like. And in a picture in the middle there, you can see what our zeolites synthesized, how very perfect they are. And they're sold either as a powder or as beads or pellets. Next slide, please. So here are some applications of synthetic zeolites. And it takes advantage of the fact that they can hold cations like heavy metals or ammonia or radioactive materials or carbon dioxide, and they can sieve them out. So for example, they're used as catalyst in the oil and gas industry. And one of the biggest current use of zeolites is in detergents. So we all know that phosphates have been, from detergents, have caused all sorts of problems in the waterways of the world. And in about half the world, they're now banned. Once you ban phosphate, you have to have another material in there to soften the water when you're doing washing. And zeolite is that material. So that's the biggest current application of zeolites. But that's an application that is not very demanding in terms of the quality. And so most of those zeolites come out of China. But there are other applications that are very demanding. For example, water treatment, where you're removing radioactive waste, PVC heat stabilizers, carbon capture, which I'll talk a little bit more about later, and animal feed supplements, where the absorbent nature of zeolites enables them to absorb mycotoxins in animals' guts, very important in terms of the animal's health and in the food chain. Next slide, please. So I'm going to talk particularly about carbon capture applications for zeolites. Now, at the moment, the market, which we'll talk about a bit later, which is already a significant market for zeolites, does not include any application of them as a carbon capture material, but they are well known in science and in developing companies as a key candidate for carbon capture processes. And so you can see here, there's two ways that can work. One is that they can capture and hold the carbon dioxide, and then you simply take that zeolite with the captured material, you change the pressure and the temperature, and you push it out, and then you can move it to another site. The other way is that they can be used as a membrane, and that is that the mix of carbon dioxide and other gases goes through a membrane, and the carbon dioxide is held while the others go through, and therefore you've separated them and you can capture them in other ways. So we all know that there's a push at the moment from our own government, but globally, to move forward carbon capture and storage solutions. And the key area that actually has not been well solved is the capture side of it. The storage and the use and turning it into useful materials has been pretty well established. but it's no good unless you can capture it at the right price. And that's what we are working on a program with our partner UQ, our partner and our one of our significant shareholders, the University of Queensland, has just started a program with us to evaluate different types of zeolites to work out which is an optimum type of zeolite to use in carbon capture, build a database, and apply our patent pending low-cost zeolite synthesis technology to deliver commercial CO2 separator solutions. Next slide, please. Another important issue in the clean tech sector is how do you deal with waste from all of those materials that we've been hearing about earlier in this program that we need for batteries and other renewable energy processes. And we've patented or patent pending, we're going through the process, a novel process to using zeolite, producing zeolite from leached spodumene residue. So what that means is that, you can mine these materials that have aluminosilicate residues and using our process, turn them into a very useful and valuable material. And in particular, zeolite type 4A and molecular sieve type 3A. Next slide, please. So I've talked about our patent pending technology. Let me give you a bit more detail of it. The University of Queensland Chemical Engineering team has demonstrated, and this is still at lab conditions at the moment, although we have announced that we're moving towards pilot demonstration, up to 70% reduction in energy consumption. Now, I told you that about 80 years ago, the process for developing a synthetic type of zeolite was developed. And essentially, we make it the same way now as was done then, which was fairly expensive raw materials that are reacted together in a way that takes quite a lot of energy and quite a reasonable amount of time, has some gel residues that are not very nice. And what UQ have done is they've started from scratch, and they've started from a kaolin clays and other residue materials that have got aluminosilicates in them, developed a process that's reduced in energy consumption, about an 80% reduction in production time, significantly less byproduct waste, and yet all while using fairly conventional commercial plant. So we were up in Brisbane just earlier this week, and saw the room where the pilot plant is being planned to be installed. So progressing well on our piloting of our patent pending technology. Next slide, please. Just a very short slide on the market, because this is not my expertise. If Peter Zato was speaking to you, he would give you a much better discussion about this. But let me just tell you that detergent grade, as I said, is not terribly pure. And for a detergent grade zeolites at about $600 or $700 a tonne, bit more expensive, bit better grade required for heat stabilizers, for PVC, $725 to $875. But what the area where we are going to be principally working is in the high value molecular sieves, where you need very pure and very well ordered zeolites, which is what our process produces. And you can see there that 3A, 4A and 5A molecular sieve grades have got prices of around $2,850 to $4,000 per tonne as beads, and $3,000 to $3,785 per tonne as pellets. And we have synthesized all of these grades at those levels of purity from our process in the lab. And you can see here that there's a bit of a graph, analyze it at your leisure. What it tells you is that the majority of the value in zeolites, and the zeolite market is already about $2.6 billion globally. And that's without all of these exciting new areas coming in. So we're selling into a market that exists. where we can satisfy existing requirements, and we are developing other new products with partners that will take us forward into brand new areas of zeolite application. Next slide, please. So just in summary, zeolites play an important role in a cleaner and safer environment. They're an effective substitute for harmful phosphates. As catalysts, they increase process efficiencies, and that of course decreases energy consumption. They can act as solid acids and reduce the need for more corrosive liquid acids. Their absorbent qualities see them used widely in water treatment, for example, heavy metal removal. And finally, as redox catalyst sorbents, they can help remove exhaust gases and CSCs, as well as, of course, having a very exciting future in carbon capture and storage. Next slide, please. Oh, and actually, yeah, there we go. Done.
Thanks, Sylvia. Right on time. Well done. This is complicated for the average investor to understand. Can you simplify how exciting this opportunity is for the average investor?
I think there's a thematic about how in Australia we take all of our raw materials and develop the processes, so we're value adding. So we sit right in that value adding space where I think we and the government want to go. So we take either waste materials or very low value kaolinic clays, and we put them through a patented process and come out the other end with a material that has lots of exciting uses, as well as a good solid existing market. We're not selling into it's not quite like the battery materials space where, the market is not that strong yet, but will be enormous. In our case, there's already a very strong market that we can play well into.
And on your patent pending technology, you've kind of demonstrated under lab conditions at the University of Queensland. How do you know that you can scale into a commercial production facility, and what sort of timeline?
So there's two things to know about how you scale things up. One is you need to do it stepwise, one step at a time. So the risk in scale up is to taking from a lab to a huge facility. We're not doing that. So we're currently at bench scale, just demonstrating what we did at lab scale. Once from bench scale, we'll go to a small pilot plant. From the small pilot plant, we'll go to a mini plant, which will still probably produce material that will have a material sales value. And then it can go to full-scale production. So we have a philosophy of doing things in a very ordered way and not taking engineering risks. Now, we also have an advantage that it's a simple process, that the actual kit that we need to buy is there available from all the standard suppliers. This is about what the UQ work has been very clever in understanding the process of making a zeolite, and it's been therefore around making sure that the temperatures and times and processing and handling and all of those things, which are patented, but using very standard equipment. So the risk therefore is low, very low.
And how do you achieve your kind of competitive price production of your synthetic A-grade zeolites? And can you just remind us again the size of the market?
So the market's about $2.3 billion at the moment for type A zeolites, and so that's the current market. And in terms of how we will, of course, one has to go through the steps of bench, pilot, mini plant production, but we have medicine modelling by our engineers that's taken the data from the lab that UQ have produced, that is using those figures around about those very significant reduction of both energy and production time. And as we all know, if you have a pretty cheap raw material set, which we do, if you have low energy requirements and low production time and low costs in residues, then and a philosophy around recycling reagents, low prices just can't fall out of that.
And are there any new zeolite uses that could expand dramatically as cost of productions fall and quality is improved?
I mean, I think certainly carbon capture and storage is a very exciting opportunity. I think expanding its use in animal feeds is exciting, and I think, and this is a bigger call out, but in soil remediation, that will need us to drive the price down. But we're having some discussions around how it can. Zeolites are already used. Natural zeolites are already used in soil remediation, and it would be a better job if it was using proper synthetic zeolites. And if we can get the pricing structure right, then protecting the barrier reef, for example, a sieve that keeps the bad stuff out of going into the barrier reef. These things are all possible if we can get the pricing structure right.